Hey guys, we're going to start our examination of non-renewable energy resources. And of course, a great place to begin is with petroleum or oil. For good reason, right? Oil supplies a third of the world's commercial energy and over 40% of the energy used in the United States. So it's sort of the lifeblood of our economy, right? I think this image is quite symbolic about how the world is sort of awashed in oil for many reasons, right? It's incredibly versatile, right? It powers vehicles, heats our homes, provides electricity, and it's a necessary ingredient in a lot of ways in a variety of products such as asphalt, plastics, and pesticides. It's also very energy dense. And I think our economy and infrastructure has revolved around it. So it has perpetuated its use without a doubt. But just where has this oil come from? And why are there some places on planet Earth with a lot of oil and others without oil? The history of oil is pretty fascinating geologically. Where does it actually form? We'd have to go back 100 to 500 million years, specifically during the Mesozoic era, um, when Pangea was starting to rip apart to produce a new body of water, a stagnant, warm, tropical body of water known as the Tethys Sea. This was teeming with life, prehistoric life. And to provide you with an analog as to sort of what the environment was like, I could bring you to the modern day Gulf of Mexico, right, where plankton blooms occur regularly, the process of eutrophication. We have this warm, stagnant, somewhat partially surrounded body of water. Nutrients from the land run off the land into the ocean and into the sea, where they stimulate productivity and lots of algae blooms occur. Uh, it's these plants that create these hydrocarbons. It's these plants that produce the stored chemical energy in the bonds of petroleum. So really, when we burn oil, we're burning ancient sunlight, as the producers use carbon dioxide and sunlight and water and convert it into stored chemical energy. Of course, all of this plant life in the ocean eventually dies. And when it does, it sinks to the bottom of the ocean. So plankton blooms sink to the bottom of the ocean or they accumulate. And of course, this is what makes the bottom of the ocean our largest carbon sink. Over time, this organic material accumulates to form an organic rich mud, which then gets compacted into a shale oil source rock. But it has to cook, and it has to cook very precisely. This is like the most difficult cake you'll ever make. You need the right ingredients and you need the right cook time. If you overcook it with too much heat and too much pressure, you'll get natural gas. If you undercook it, you'll get this sort of half-baked tar sand. Not only do you have to cook it properly, but you also need some other geologic structures for it to be stored over time. So the source rock cooks, and eventually the hydrocarbons crack, releasing that light, sweet crude. But then you need a reservoir rock that sits on top of it to store it, because oil is low density. It wants to rise. So typically a limestone rock and these anticlinal folds allow the oil to absorb into the rock and then get stored into some of these cavities where it can pool over millions of years. Furthermore, you have to cap that, right? You need an impervious rock layer to cap it so that the oil doesn't continue to migrate and just simply spill out onto the surface. Millions of years later, of course, humans come along and we drill into it, and placing the well there, the oil falls into the well where we then pump it to the surface. Geologists typically look for oil deposits using aerial photography and satellite imagery And they look for these gentle folds in the landscape, and they study the surface and subsurface geology. And it turns out there's only a few select locations on planet Earth that's going to have a lot of oil. And the majority of them are, of course, found in the Middle East. Saudi Arabia has the largest supply at 20%. Of course, it was the Arabian Peninsula that sat below the Tethys Sea. Number two is Iran. Number three is Iraq. Now, we know that these countries are not politically stable, and so that has resulted in a lot of bloodshed and warfare as the United States and other countries have attempted to sort of control some of these resources over the time. Now, the United States has realized that its dependence on foreign oil is not stable due to the political instability of the region. And so we've looked after and sought our own energy resources of oil, gone to more remote, inhospitable environments like Gulf of Mexico and the Alaskan permafrost and North Slope. As a result of increased U.S. production, the United States is now the largest producer of oil, despite the fact that we only contain or have about 1.5% of the oil reserves on planet Earth. Nevertheless, we use 20% of the global oil. So we are big users, and we're users for a lot of reasons, right? We said there's a high energy density, our infrastructure is well developed, we can transport it quite easily. And it's subsidized, right? Our economy is built on it. So we've subsidized the industry to keep the prices artificially low. And I say artificially because, of course, it's not going to include some of the environmental externalities that may harm the environment or even harm human health. Our supplies are, of course, limited, and many argue that we are currently past peak production. And most speculate that our oil supplies will no longer be viable or economically worth our while to extract by the year 2050 or 2100. And the reason there is because the net energy yield, while high right now, is going to decrease as we have to use more energy to extract more and more oil from more remote locations of lower concentrations. It's going to reduce the net energy yield overall. Once we pull the oil from the ground, we have to then refine it. So we process the oil, and we do this through a process we call distillation. In other words, we boil it, we cook it. And based on its boiling point, we get a variety of different products. And so we use these 100-foot fractionation towers where we boil the oil, and the more volatile parts tend to sort of hover close to the top, while the other ones that are more stable under higher temperatures sink to the bottom. And depending on what product we want to get from the petroleum, we simply pull it out at its respective layer. We actually go further than that, though, because we have a lot of non-fuel products that are the result of molecular engineering, right? So we have scientists in the petrochemical industry that reconstruct these hydrocarbons. They actually crack them at the molecular level and then stick them back together. And in this way, we get hundreds, if not thousands, of additional chemicals that are used in our modern world. Pesticides, for example, paint, and of course, the ubiquitous plastic. There are many disadvantages associated with oil, many of which are environmentally related. Certainly, we do have a well-developed infrastructure for transport, but sometimes that transport goes wrong, and we only have to think of oil spills related to cargo boats or perhaps offshore wells being disrupted. Furthermore, it also releases carbon dioxide, which is a greenhouse gas. So oil is a contributor to climate change, as it is ancient carbon after all. And then finally, in urban areas where there's lots of automobile traffic and the combustion of gasoline, there's lots of photochemical interactions in the atmosphere during rush hour to produce photochemical smog, a ground level ozone that is harmful to human health and reduces visibility and destroys vegetation. We'll stop there for today, guys. See you soon.